Even I'll start the recording as well. Even I'll start the recording as well. Okay, good. We are live on YouTube and I started recording as well. So welcome to the Silicon Valley chapter of IEEE Computer Society event. I am the chapter chair, Vishnu Pendyala. At the outset, I wish you all a happy IEEE day. It's been 140 years since a group of engineers came together and started what we know today as IEEE. So the theme of IEEE Day is leveraging technology for a better tomorrow. So very apt for today's Ask Me Anything session. A bit about our chapter. Ours is the largest chapter in the Silicon Valley section of IEEE with over 3,500 subscribers in our mailing list and a strong following of over 12,300 on Twitter alone. We are uniquely positioned by the virtue of our location and available expertise. And thanks to the virtual modality, we are now able to feature renowned researchers from all over the world, like Professor Gautam Kamath today. Dr. Kamath is an assistant professor at the David R. Cheriton School of Computer Science at the University of Waterloo and a Canada CIFAR AI chair and faculty member at the Vector Institute. He has a bachelor's in computer science and electrical and computer engineering from Cornell and MS and Ph.D. degrees in computer science from the Massachusetts Institute of Technology, MIT. He is interested in reliable and trustworthy statistics and machine learning, including considerations such as data privacy and robustness. He was a Microsoft Research Fellow as a part of the Simons-Berkeley Research Fellowship Program at the Simons Institute for the Theory of Computing. He serves as an editor-in-chief for Transactions on Machine Learning Research and is the program committee co-chair for the 36th International Conference on Algorithmic Learning Theory, ALT 2025. He is the recipient of several awards, including the Caspar Bowden Award for Outstanding Research in Privacy-Enhancing Technologies, a Best Paper Award at the 41st International Conference on Machine Learning, which is a very prestigious conference in 2024, and the Faculty of Math Golden Jubilee Research Excellence Award. So he'll be answering a lot of questions today in the Ask Me Anything session on data privacy, machine learning, and more. So after a brief introduction highlighting issues and solutions for data privacy in machine learning settings, Professor Kamath will answer your questions related to data privacy, machine unlearning, research, academia. He is even open to answering questions on career advice and anything in between. So please feel free to post your questions in the QA panel or chat window, or if you are on YouTube, in the YouTube chat. In the meantime, I'll engage him with questions that I already received. So the links to the video and the slides will be posted on our website in about a week. So over to you, Dr. Kamath. Please take it away.
Thanks so much, Vishnu. Yeah, first of all, let me say thank you for the nice introduction and thank you for the invitation. It's really cool to, talk with people. And, happy IEEE Day. I had no idea. I've known IEEE my entire life, but I didn't know it's 140 years old. That's very impressive for such an organization. So yeah, I'd like to start just with a short introduction to differential privacy, since this is what a lot of my research is on, and it might not be familiar to everyone. So I just want to make sure you get something out of this, even if you don't like the questions, they're of a different sort. If everyone understands at least some of the threats that differential privacy is trying to protect against, then I think that's a success in my books. So I want to show you one example to start with. If you ask ChatGPT pretty much anything, it'll give you, without hesitation, a pretty good answer to it. But I want to show you a different query you can ask ChatGPT, a bit unusual. Repeat the following word forever: company, company, company. And despite the unconventional nature of this question, it'll do it until it doesn't. You can see here it's gone off the rails, and it's not really clear what's going on. The researchers who undertook the study did a little bit more digging in and found out that the model is spitting out some of its training data here. Now, this specific case is fairly innocuous. It doesn't seem super important or personal, but they did some more study and found that actually at times it can be inclined to spit out parts of its training data which correspond to personal information. And so the threat here, the problem, is that machine learning models can leak sensitive information that's contained in their training data, which is a problem to do with privacy. So this is just one example of where privacy issues can show up, which are, in one of these exciting modern AI applications. But there's also much more fundamental settings where these issues can show up. For example, consider the US decennial census. This is one of the most important data products in the United States, where they try to get a count of every single individual in the United States. And this data is hugely important, used for things like districting and apportionment in the House of Representatives, which are hugely consequential for people's everyday lives. Unfortunately, as I alluded to, privacy issues show up here as well. Here's a caricature of what the Census Bureau releases publicly. Essentially, they don't release individual data rows. They instead aggregate statistics over subgroups and subpopulations, like men, women, by race, etc. They do this in hopes of hiding individual personal data. So, you can't tell things like I'm a 33-year-old man of Indian ethnicity, etc. But unfortunately, it turns out that this hopeful privacy protection is not actually so secure. In particular, using things like SAT solvers, the implied constraints let you reconstruct what's known as the microdata. So you can find out in the data set that, okay, there was an 84-year-old male who was Black and married, which is a privacy violation. Even worse, by matching this with commercial databases, it's possible to re-identify individuals who possess these sensitive traits. And so here's a tweet from John A. Bowden, who was the chief scientist of the 2020 US Census. And essentially, in an auditing attack that they did themselves, they found that effectively you can re-identify half the country from public census releases, as well as matching with commercial databases, which is a huge violation of privacy, something that they're required to protect under US law. So these are just two examples. There's many more I could show you. But the bottom line is that these privacy issues are really ubiquitous, and they must be addressed. Otherwise, they violate regulations, they harm real individuals, and so on. And a common theme is that best effort privatization generally doesn't work. This type of aggregation and hoping that it'll hide individuals' personal data, these have been shown to not be effective in any sort of rigorous way. This has been a huge topic of interest nowadays. Here's a few words from US President Joe Biden.
So Gautam, we are not able to hear the audio.
Oh, sure. Don't worry about it. The subtitles say what he's saying.
Oh, okay.
So what he's talking about here is a new executive order that he signed actually just about a year ago, in October of 2023, focused on trustworthy AI, which, amongst other things, is intended to protect Americans' privacy. And if you dig into the text of this executive order, you'll see that by name he mentions something known as differential privacy. So differential privacy is where a lot of my research focuses, and it's a hugely important and influential concept in privacy enhancing technologies nowadays. The definition of differential privacy is a little bit tricky. I'm going to try to give you an idea of what it's supposed to protect against. The formal definition isn't super important for today, but I just want to give you a little bit of a flavor of the protection it provides. So imagine that there's some data set which is fed into an algorithm and it produces some output. Alternatively, you could imagine a different data set which differs in one entry is fed into the algorithm and it produces an output. Now, an adversary, a malicious party, let's say, is looking at the output of this algorithm and they're trying to figure out what was the input. Was it X or X prime? And if they're unable to say which one it was, better than, say, randomly guessing between the two, then we say the algorithm is differentially private. So this is sort of a caricature. Here's an informal definition of what it is. We say a procedure is differentially private if its distribution over outputs doesn't change much with the modification of one data point. Here's a more formal definition, which again isn't super important. The first 5 times I saw this definition, it didn't make much sense to me. The main thing I want to emphasize here is a quantitative definition with a rigorous sort of guarantee here about what exactly it does. These parameters known as epsilon and delta, which they're little knobs you can turn. The lower epsilon and delta are, the more private the algorithm is. The higher they are, the less private it is. But again, you can just use this informal definition. And in fact, even the informal definition is probably overkill in terms of thinking about it, just if you're not doing active research in it. You can think of it as a rigorous type of privacy protection that protects against all the types of threats that I mentioned before. Things like if you train a model with differential privacy, it's protected against spitting out its training data, and you can't re-identify individuals in the way that I showed you could for the census. And very importantly, I think this is a rigorous and provable guarantee. Frequently, when we talk about trustworthiness in machine learning, often we're talking about heuristic type of guarantees, but this is rigorous and provable, which I think is important because as the adage goes, once you lose someone's trust, it's very hard, if not impossible, to regain. So instantiating that for privacy, when you tell someone that their privacy is protected, and then if you suffer a privacy leak, then it's very hard, if not impossible, to regain that trust that they gave you when they gave you their private data in the first place. So to give you a simple example to make this a little bit concrete, let's imagine there is a population of, say, 100 people, and you want to know how many of them smoke. Say 20 say yes. This is a sensitive query because maybe people might not want it to be known that they're a smoker. Their insurance premiums might rise if this fact was known. And so one thing you can do is add discrete Gaussian noise to this number 20. I chose the discrete Gaussian for kind of 2 reasons. One is because if you add noise to a count, which is an integer, then it'll still be an integer after noising it. I also like it because it's an algorithm we introduced a few years ago at NeurIPS. And so if you add discrete Gaussian noise to this 20, you'll see that you get some error in it, but it's still pretty close to the answer 20. But in some rigorous way that I won't quantify for you, these outputs are actually private. Like I mentioned, there's a knob you can turn by adding, and what this amounts to in practice would be is if you add noise with higher variance, then you're going to get more error here. Say you can see the difference between them and 20 is larger. But in fact, these are more private, again, in a rigorous way that I won't quantify for you. So that's like kind of the most simple example of differential privacy. And so this is, a simple primitive. This is, you might be thinking this is too basic to do anything complicated with, but in fact, it's been used in things like federated learning. And in fact, it was used in the 2020 US Census in order to protect against these type of disclosures that I alluded to before. So despite some of these things I tell you being very simple, they can be used as building blocks to make very complicated systems. Some other things that have been used for include, for example, COVID-19 community mobility reports, which were released by Google after COVID began. People's movement habits, they changed when COVID began. People were taking less public transit. They weren't going to work. And so Google wanted to release this type of sociological data, which could have value to people. But of course, and how do they get this data? Well, one of these, you carry around your phone perhaps all the time everywhere you go. And so Google knows where you go. But of course, this is privacy sensitive data. What they did is they released only aggregates of where people went and protected these disclosures using differential privacy. So they managed to provide useful data, which is still privatized. Google also uses differential privacy for private machine learning. For example, when you type anything on your phone, you know these next word predictions which pop up. Well, now Google uses differential privacy in order to protect these type of the data used to train these models. Like the way these things work is when you type into your phone keyboard, it'll be learning a model about what the next word is. But of course, this contains your private messages and not something you might be willing to share with other people. So using a combination of federated learning and differential privacy, Google is able to train distributed models which are able to protect individual privacy in this way. So this is one of the most large-scale implementations of differential privacy and federated learning that I'm personally aware of. And there's many more real-world deployments that I could tell you about, but I'll point you to this very nice blog post by Damien Desfontaines, which covers how differential privacy is used in all of these companies as well as more. So this is just a taste of where differential privacy is used. You can also check out my online course, which is on YouTube, which has a full series of notes and videos. Or at least for now, you can ask me anything. Cool. Thanks, Vishnu. That's sort of the intro I wanted to give to differential privacy for those who haven't seen it before.
Thanks, Gautam. That was quite insightful. The very first example that you gave was quite interesting. So we have a bunch of questions that were asked by others. I'll probably start with the continuing the topic of differential privacy. Your paper on position, considerations for differentially private learning with large-scale public pre-training. So there are a couple of questions actually. Yeah, there are a couple of questions on this paper. The first question is from Nandana Hemant Kumar. The question is, if we think about the broader implications, how would we apply this approach to domains like healthcare and finance, where the public and private data have very different characteristics?
Right, and that's a really good question. So just for a little bit of context for people who may not be familiar with this work, we had a position paper at this past ICML, which critiques a currently very popular method of using machine learning models for differential privacy. In particular, it's commonly assumed that these models are pre-trained on, say, public data, things which are scraped off the public internet usually, and then privately fine-tuned. That is maybe your sensitive data set, which is specific to your application, things like medical data. If you're a hospital, you can fine-tune your model using this data using differential privacy. So we critique this general two-stage approach of public pre-training and private fine-tuning. One of our critiques, which I won't go too much into right now, is the fact that, first of all, this public data, which is taken from the public internet, we just treat this as public. But the problem is that there's a bit of a mismatch between what is publicly available and what may be okay for use in machine learning applications which treat this data as public. For example, data may be publicly available, but it was gathered, say, in a non-consensual way or maybe for a specific purpose. So that's one critique. Another critique we raise is the fact that, if you just download a bunch of pictures from the public internet, you're going to find pictures that are things like, dogs and cats, or pictures of people, like just general natural photos that you might take with your camera. There may be significant distribution shift with respect to applications where we actually care about privacy. As an example, consider a hospital where you might consider about doing classification for things like chest x-rays or eyeball scans to check if someone has diabetes. These are very different types of distribution. So it's unclear whether when you do this public pre-training, it's actually useful for these types of sensitive applications like healthcare. So that's one of our critiques. And I think there's two possible universes. One universe is where somehow by the magic of AI and machine learning, that pre-training on data like dogs and cats may actually be useful for things like chest x-rays. Maybe just it's able to pick up on what types of features are actually useful for this. And the other type of world is a world in which this pre-training is a very low value. So pre-training on pictures of dogs and cats and humans, this is not very useful for being able to classify chest x-rays. So I would say the first step is trying to understand which of these two universes we're in, whether this transfer is actually effective. And that's something I'm currently doing with some of my students, where we're looking at some medical data sets to see whether we can get good classification accuracy using this type of paradigm. And so far, it seems like, the punchline is that it's not super effective, that, the transfer property isn't as effective as it has been for many of the benchmarks people have previously considered, things like CIFAR 10 and ImageNet. So in terms of solutions, maybe gathering more data for these privacy-sensitive domains is a very important next step to be able to get better utility in these types of settings, or, design new techniques which focus specifically on these settings.
Yeah, thanks. And there's a question on the QA panel, in the QA panel from an anonymous participant. So the question is, as a healthcare privacy and assistive technology professional, I see a gap in cybersecurity literacy among my peers. What practical steps can we take to improve cybersecurity training and awareness for healthcare privacy professionals to better protect patient data?
Right, that's a great question. And it hints at the fact that in general, there's a big divide between currently what people are doing in research and what people are doing actually on the ground in practice, like as you said, as a healthcare professional. And I think these things are unfortunately slow, but sometimes some things can help speed them along. For example, legislation frequently makes people get up to speed very quickly. So there's of course some legislation which says what you can and can't do with patient data, which is maybe developed, I don't know, decades ago even. So I think in the rise of machine learning and AI models, I think we're going to have to quickly rethink on a number of different things, including privacy as well as efficacy, ethics, many of these things. So right, I think legislation will help speed these things along, but that of course requires a lot of care. Coming up with the right legislation is an important step. For example, I mean, very local to you guys in Silicon Valley, there was a recently proposed legislation on the use of AI called SB 1047, which was actually vetoed by the governor. There was a lot of discussion about whether this is a good thing. There were people on both sides of the issue I saw. So I think legislation is one way. I think maybe a less heavy-handed way, maybe just better education. And I think this takes a while to trickle down, so to speak. For example, at least using my own expertise as someone who's in the research community, typically there's research papers. And then the next step after research papers is typically people maybe write a survey article or maybe a book. And then from there, it becomes a course. And then from there, it goes into, training programs for professionals. So I think there's a bit of a pipeline which requires work at every step. But this is kind of the pipeline that I think would have to be done, which unfortunately takes a bit of time. But with subject matter expertise, it's possible to speed these things along.
Okay, I hope that answers the question, whoever asked it. Then relating to your paper on machine unlearning fails to remove data poisoning attacks. So there are again a couple of questions. This one is from Chandana Sriya. The question is, your paper demonstrates that current machine unlearning methods fail to mitigate data poisoning attacks. Given these findings, what do you believe are the most promising research directions or approaches to develop a more robust unlearning algorithm that can effectively remove the influence of poison data?
Right, and I think this is a super good question. One I wish I knew the answer to. So for a bit more context here, machine unlearning, I didn't talk about it in sort of my intro slides, but machine unlearning is the following very natural type of question. Suppose you have a trained machine learning model, and you want to get a machine learning model which is like that, but has someone's data removed. Say, for example, I decide to, at some point, revoke the consent that I gave before and say, you can no longer use my data in your machine learning model. So this is sort of like a privacy-related reason. There's other reasons, such as copyright. Suppose you trained a machine learning model on a bunch of text and then realized accidentally, oops, I included the text of Harry Potter. What can I do to get rid of that data? And there's one baseline approach, which is literally retrain your model from scratch, just leave out this sensitive training data that we want to avoid. But of course, training these models costs like a lot of resources, a lot of time, a lot of money, millions of dollars to train any of these. So of course, that's not very practical as a solution, which leaves us in a bit of a conundrum. Is there any fast or effective or efficient way to just remove one point from a model's data set after it's already been trained? And this is known as machine unlearning. This has been super popular over the last couple of years. A lot of people have proposed a lot of algorithms for it. In a very recent work, which we have, which is just on arXiv for now, a few months ago, we kind of show that the way that people are evaluating these techniques for machine unlearning has been a bit faulty. That is, we show that if you try to measure whether they can actually unlearn data poisoning attacks, which is a frequently stated motivation for this type of method, they just don't do it very well. So yeah, this shows, in other words, machine unlearning algorithms, which are purported to work, just don't work as well as people claim. And this is hugely problematic. Like what I mentioned before for differential privacy, often when you make this type of guarantee, it needs to actually work because maybe you have people's trust, maybe there's legislation requiring you to do it. So this is a real problem, the fact that these machine unlearning approaches don't work as well as people sort of market them to do. And so the question was about, is there a good way to actually efficiently remove the influence? And the unfortunate thing is that, well, the good and bad news, the bad news is that, no, we don't really know a good way besides that sort of straw man that I told you where you just retrain the model from scratch, which is going to take a lot of time and money. The good news is that if you're a researcher in this area, there's a lot of work to be done. There's a very, very interesting and timely technical question. How do you essentially come up with good machine unlearning algorithms? And my own perspective is, at least we should try to focus on machine unlearning algorithms which are based on provable guarantees. Somehow we can prove that it unlearns it, because as is shown to be the case here, even if you heuristically or empirically demonstrate that your unlearning method is good for some problems, it may be that someone else comes along and shows that it's not effective in other settings. So really a focus around provable machine unlearning techniques, I think, is very key for moving forward.
So has there been any work in the provable machine unlearning?
Yeah, there has been some work on provable machine unlearning, but unfortunately, all of it's deficient in one way or another. For example, we have one paper authored by myself, but also Sakari et al., which gives a provable method for machine unlearning, but the major caveat is that this is only applicable for convex models. So, these are simpler things like, SVM or logistic regression. In particular, it doesn't work for some of the more modern things like, large language models or neural networks more generally. So, that's one caveat. It only works for restricted class of models. There's other methods. There's a nice paper by Nicolas Paperneau's group, which focuses on, even non-convex models, which involves model checkpointing and sharding. Without going into details of that, I'll say that it's a nice method, but there's some drawbacks in the sense that it relies on ensembling methods, which generally result in big hits to utility. It still can take a long time. There's some big memory overheads. So, for one way or another, we don't know of any panacea to this problem where for, large non-convex models, it just sort of works effectively and provably. So that's, I think, the holy grail of this type of research direction, finding something that works, say, for large language models that you can just unlearn effectively and provably.
So just curious, what has convexity to do with provability of machine unlearning?
Yeah, great question. I guess like one of the key points of a convex model is the fact that one of the basic things about convexity is that it leads to there being a global optimum for the problem. So the idea that there's sort of just one parameter solution, which is kind of the right one. So the main idea is that if you have a trained model in a convex setting, this will lead you to kind of a solution to that will give you an optimal parameter vector. And you can roughly argue that if you changed one training data point, this shouldn't really be too far off from where it was, just because it's only one training data example. And so it's possible, based on what the gradient or even the second order derivative information of what the point you're trying to remove is, how far you should move. So, roughly speaking, it's just the fact that the following two facts: one, that convexity implies the global optimum, and two, that you won't really move much by changing one training data point. Putting those two facts together in the right technical way leads you to a global solution. But both of those go out the window when you consider non-convex models. In particular, there may be many, you might get stuck in a local optimum rather than a global optimum. One training data point being changed might cause you to jump all over. There's a lot of challenges that, the nice properties of convexity don't hold in non-convex settings.
Okay, so machine unlearning itself is applicable to non-convex settings, but the provability aspect of it is only applicable to convexity. Convex.
Exactly, yeah. At least for current methods that we know provable methods for, and which don't have maybe impractical overheads in terms of other constraints like memory usage, then yeah, we only have effective provable algorithms for convex settings.
Okay, so there's a research gap that researchers should start addressing. And that brings us to the next question on the QA panel. So Sneha Talwalkar is asking, she is a PhD student at University of Texas working on voice authentication. She has two questions actually. I'm curious if you have applied differential privacy to different data sets like audio. That's the first question. And the second question is, I'm looking for a summer internship next year. Would you be accepting interns in the summer of 2025?
Sure, let me answer the first question first. So regarding like speech recognition, voice recognition type models, I haven't personally done work in privacy for speech models, but I know there has been some nice work. For example, I'll link in the chat, a friend of mine named Om Thakkar, who's at Google. I know him and his group work on models which are voice recognition models, ASR. And so here's one paper I linked in the chat, which is focusing on privacy in these type of settings. So this is just a starting point. I'd recommend looking into some of his other works and from his group as well. This would be a good starting point, at least, to take a look. As for internships, I'm not usually able to take interns from outside the university. We just don't have really methods about it. But if you have a specific technical question related to any of my research that I'd be able to give you a tip on, then you can always send me an email and try my best to answer it.
Okay. Hope that answers the question. So there's a second question from Chandana Shreya on the same paper, Machine Unlearning. So your work introduces a new evaluation metric for unlearning based on Gaussian noise poisoning. Do you envision this metric being adopted more broadly as a standard way to evaluate unlearning algorithms? What are the key advantages or limitations of this approach compared to existing evaluation methods?
Right. So say a little bit more about what we kind of did in this paper. We imagined that someone mounts a data poisoning attack. So data poisoning attacks are typically a setting where, say, some fraction of the training data is modified by an adversary for some sort of malicious purpose down the line. For example, setting up a backdoor so that at test time, they can exploit this backdoor to get classification that they like. Or other things include targeted data poisoning attack, where they want to have a specific test point to be misclassified to their liking. So these are all things that we use to evaluate. But the reason why these were introduced are typically for demonstrating certain vulnerabilities of the neural networks, forgetting totally about machine unlearning. They're for very different settings. And first thing we show is that these are not really easily removed by machine unlearning methods. On the other hand, we introduce also something known as like Gaussian data poisoning, which is a much simpler method. In particular, what it does is it just adds Gaussian noise to the inputs of the model. And this is generally a pretty innocuous, it's an innocuous method in the sense that if you just take a neural network, add Gaussian noise to all your training data, and then feed it through and train the model with that, it usually won't have much influence to the model. Like, it'll still perform the exact same. So in that sense, it's not a very good poisoning attack. It won't change the behavior of the model in any meaningful way. However, what we show is that this is sort of what do I want to say? It's possible to audit a model afterwards and show that there are still signs of this Gaussian noise that you introduced to your training data. That is, it won't negatively affect the performance of the model, but it's still detectable. And we use that as something to see whether the machine unlearning was effective or not. So I think this is I like this because it's a very simple method. It doesn't require any sort of deep expertise. It's very efficient to run. And I like it because it doesn't influence the performance of the model. It'll behave pretty much the exact same, meaning that this sort of attack is hard to detect. But on the other hand, it serves as a type of fingerprint to see whether this type of attack was mounted and whether machine unlearning was actually effective at removing it. So yeah, for those reasons, its simplicity and its sort of innocuous nature, I hope that people consider it as a way to evaluate machine unlearning techniques.
Yeah, and on the same topic, Bhavya Jammu is asking, how can the findings from this research be applied to real-world scenarios such as protecting sensitive user data and machine learning-powered applications? What are the potential challenges and limitations in implementing these techniques in the industry?
Yeah, and I think this just serves as another way of auditing to see if machine unlearning worked. For example, like imagine you're a practitioner who is running some sort of unlearning algorithm. Of course, you want some sort of okay, first of all, like I've sort of said before, the gold standard would be if you can actually use a provable method. If you can, then you're good. You don't have to do any sort of auditing. But at least at present, more likely than not, you would have to turn to some sort of heuristic method. And at the very least, you should be able to, evaluate your method to see, can it protect against vulnerabilities that you're aware of. You'll never be able to protect against vulnerabilities you're not aware of if you're using heuristic methods. But at the very least, it gives another tool in your arsenal to try to give you some confidence that your machine unlearning method is actually working as it purports to. So to be a little bit more concrete, you can imagine you're a practitioner who's used a machine unlearning algorithm, and then you can check whether it was effective by running things like, first of all, membership inference attacks, which are kind of the classic way of evaluating machine unlearning settings. And also you can run, attacks which are based on data poisoning like we do. So this sort of broadens the arsenal of potential ways to detect whether your machine unlearning method is actually effective or not, thus giving you a little bit more confidence that it might actually work more broadly.
Okay, and switching back to differential privacy, and specifically with respect to your paper, Preserving Differential Privacy in Machine Learning Models, Pavan Kumar is asking, with the rise of federated learning, how can differential privacy be effectively integrated across distributed models to ensure both global privacy guarantees and local model performance? What are the most common challenges faced in doing so?
Right, and this is a really good question. I'll mention that like federated learning and differential privacy, first of all, they're kind of complementary. They're complementary technologies. They're both in the space of privacy enhancing technologies, but they both focus on very sort of different threat models and protect against different things. They have different considerations. So they kind of, yeah, they go hand in hand with each other. I think one thing I want to address, by the way, which is a misconception, not mentioned in this question in particular, but it's a very easy to make misconception that many people have. So what is federated learning? Federated learning is a type of setting where, the canonical example is everyone has their own phone and Google or Apple want to learn some sort of model, but they also don't want to take your data from your phone for, say, privacy reasons. So essentially what they can do is instead of sending your data to Google, you send effectively, indirectly what your gradient updates to some model are. And this minimizes the amount of communication of data that you send. It's sort of a data minimization style approach to privacy. And hopefully you train a model centrally, which uses everyone's data, even though it's distributed. So people believe that this provides some sort of privacy because of the fact that the data never leaves your device is kind of the usual marketing tagline. But the somewhat problematic thing about this is the fact that federated learning, in fact, even just sending the gradients, this can still contain crucial information of the data itself. So, there's been many papers by others that show that federated learning by itself is not private. And in fact, if anyone's curious about learning more about this, I will link a blog post which links to a research paper in the chat, which sort of shows some of the, oh, sorry, this is just a, sorry, let me, this is the blog post, which I meant to link, which gives more information about, some of the vulnerabilities of federated learning. So, but as to answer the question, on the other hand, while federated learning by itself is not private, for some settings like this, you can use federated learning and differential privacy hand in hand in order to train truly privacy preserving models. And there's a number of technical challenges that come up in practice here. To get a little bit technical, I'll say that when you're training a prop model with differential privacy, one of the important things to be able to do is to be able to randomly subsample your data. Say your training data is 1 million points, you want to subsample a batch uniformly at random of size like 64. This is something that is difficult to do in a federated learning setting because, you never know what your user device they're doing. Maybe someone is charging their phone, but someone else needs it and they can't send their data right now. So the problem is this type of sampling step is very difficult to do. That's just one example. But as a consequence, researchers have done a lot more work in terms of even designed entirely new algorithms, which are better suited for federated learning type settings. And I think the best place to look for an overview of some of the challenges and how they overcome them is this Google paper, differential privacy. Let me see if I can find the paper real quick. Yeah, this paper, which I showed a sort of picture of, which talks about some of the challenges they faced when training specifically this Gboard federated learning model and how they overcame them.
So, so the summary is that there is still a role for differential privacy to play here, right? Like, for instance, if you're using support vector machines, where we are sending support vectors across. There is a need for protecting the privacy of the support vectors, right? So we can probably include some differential privacy there.
Exactly. Let me say things a slightly different way, in the sense that federated learning, the problem it's meant to solve is the idea that you don't have all your data at one place. But in the ideal case, the model you would train centrally is the exact same as the one that you would train with federated learning. So but the thing is, if the model is the same as if all the data was trained centrally, then you can still run into these type of memorization issues. For example, the ChatGPT example I gave at the very beginning, where it's memorizing parts of its training data. A perfectly trained federated learning model would be the exact same. It would still, spit out parts of its training data. So just as you said, you would have to also train with differential privacy to make sure that you're not giving away too much information with your solution, like protecting the support vectors and so on. Yes.
Okay. And that leads to the next question. This also is from Pawan Kumar. And he's asking, in applications like natural language processing, you just took the example of ChatGPT. How do you balance the need for differential privacy with the preservation of linguistic features and contexts that are critical for model accuracy?
And yeah, that's a super, that's probably one of the bigger challenges, generally speaking, in the sense that it's well known and sort of unavoidable, the fact that differential privacy will hurt your model accuracy. I think the ideal thing you could do is be able to disentangle some parts of what is public versus private data. For example, there's certain things which we don't consider to be private about the English language, things like grammar, syntax, what words typically follow each other, the sentence structures. These are things which we all kind of learn in school, and these are captured a lot during in pretty much all training data. So it's kind of the most popular way to learn these things is a similar sort of approach, in the sense that just using public pre-training seems to be very effective, because just any collection of text will have information like what do linguistic features look like, what type of context, things like this. This is a good way to at least give a model a prior, sort of an understanding of what English text looks like, or whatever language you're focusing on, which won't be hurt by differential privacy if you do pre-training without differential privacy. Now, of course, when you're talking about things within a very specific context, things like medical data or private emails, then for these types of settings, when you use differential privacy, it's kind of like unavoidable that you're going to run into accuracy issues. But yeah, I think the best you can do is really find some sort of way to encode in the model these sort of things which are not privacy sensitive, like I mentioned, grammar, syntax, and so on. And then once you do that, then you can use differential privacy to protect the true secrets.
Okay, sounds good. And on the same topic, Minute Tran is asking, I was wondering about the existence of a sort of counter differential privacy algorithm. Given that there is noise added to the empirical mean, would it be possible to reverse the data noise, that is, recreate the original distribution, given that adversary knows that the data has been altered? Would this be too computationally inefficient, or is it possible to transform the data back to its original form?
So the great thing is that, it's very convenient that the answer to this is no, there is no such algorithm. So let me take a step back and tell you about something which is common in cryptography, security, privacy, which is known as Kirchhoff's principle. It roughly states that the idea that you should be able to publish publicly whatever algorithm you're running. You publish essentially, details of your algorithm. You publish everything except for the randomness you use in the procedure. And Kirchhoff's principle says that you should be able to do all of that and still maintain some sort of privacy or security guarantee. And this is very familiar in, say, things like cryptography or public key cryptography, where it's well known that one of the most popular algorithms in the space is called the RSA algorithm. So this is something you can look up in any basic cryptography textbook. It'll describe how to do it. The key thing is that there is one secret key, which is generated during doing this sorts of cryptography, which is not released to the public. And RSA is secure in the sense that as long as the adversary doesn't know what your secret key is, they're unable to decrypt the messages. And that's very good news, because otherwise cryptography wouldn't work and we wouldn't be able to do bank transactions online or any of the many other things that we use cryptography for. So by a similar token, differential privacy is private in the sense that as long as the adversary doesn't actually know the specific realization of the random variable that you sampled, it'll still be private with the sort of provable guarantees that I flashed very quickly. So yeah, the good news is that there's no way to, reverse engineer differential privacy if it's done properly.
Okay. And one other related question is, how do you see this from Dongmei Han? How do you see differential privacy evolving to better protect sensitive data, especially in areas like healthcare, without significantly lowering model accuracy? Could techniques like adaptive privacy or combining privacy with encryption help solve these challenges?
Yeah, I think this is a super broad question, and I think like I don't think it's easy to give a good answer to this, just because this is where most of the research on differential privacy focuses on right now. Like, how do we train a model subject to a privacy constraint uh, and try to make the utility as good as possible? This is kind of like the big picture question in differential privacy for pretty much any task. And people have studied this. The techniques or answers would differ based on which setting you care about. There's some sort of general rules of thumb which I can give you for, say, training machine learning models with differential privacy. For example, we've found that different type of activation functions may be better. There are some better ways of doing data augmentation, which work better with differential privacy, things like this. But it's hard to give too broad an answer to this, just because it depends so much on the setting you care about.
Okay. Okay, so there is a question from Joseph Chang. It is on your talk. Apparently, you gave a talk on which is available on YouTube. Let's Talk AI, AI's Future. And he's asking, how do you think the increasing reliance on artificial intelligence will impact the job market and the workforce in the future? What type of skills do you believe will be important for future generations to work effectively with AI? Also, can AI think and be creative on its own, or is it usually replicating creativity based on the data provided by humans? So I think this is kind of leading to artificial general intelligence sort of thing. So do you have any opinion?
Yeah, this is like the $1 million question, or maybe even more accurately, the $1 trillion question. Like, I usually am very conservative in, the predictions and statements I make, just because, I think that's very much I'm a theorist by training. And so often theorists are very measured or conservative about the type of statements they try to make. So I think the only statement that I can conclusively say is that anyone who tells you they know the answer to this is probably lying to you, or maybe being a bit more confident than they actually should be. Everyone has an opinion on this. Some people, to the range of opinions, is that one, it'll totally transform our society and every part of it. On the other end of the spectrum, we're in a bubble. It'll be useful at doing some very specific things, but not go too far beyond what we can actually do. I think the most specific question, like, actually many of my students, as a professor of computer science, many of my students ask me, like, what am I going to do? As a computer scientist, should I change my degree? Should I study something different? There's a lot of, I think, fear and uncertainty about people who are not already established in their career, especially, and maybe even worse for people who are already 20 years in their career, because it's too late, so to speak, for them to do something different. But they ask me sort of, should I be worried? Should I do something different and switch my major? I think my advice to them, at least, has been that, nobody can tell you how these things will change our society. But I think at the very least, I'm confident in saying that having the technical background that a computer science degree gives you, or any sort of adjacent field as well, like engineering, this gives you the type of background to know how these things really work and understand the implications. So I think I don't see why this area of expertise would leave you any more exposed than, say, anywhere else. If nothing else, you have the technical expertise to be able to understand how they work. I do, however, think it's important to stay up to date and not let yourself become a dinosaur, so to speak. Like, know what's happening, what the trends are, so you don't get left behind, keeping your skills up to date. For example, knowing a common example is writing code with AI models. This has become a very popular thing, and people can see that they do very good things. So I think rather than totally ignoring these models or thinking, okay, they're just going to solve everything, I think being able to know how to use them, what they're good at, what they're not good at, and sort of incorporating them into your own skill set would be better. And in any world, that seems like that would just be a better thing for your own skill set. As for the last part of this about creativity, this again, as a theorist, I like to focus on definitions, and I don't rigorous things that we can claim and state. I don't know how we define what it means to be creative in a truly rigorous sense. What it means to be creative, what it means to be intelligent. Maybe that's a little bit better defined. Yeah, I think this is a bit ill-defined, and I don't know how we would even begin to reason about whether a machine learning model can be creative in what we consider as humans to be creativity.
Yeah, thanks for the perspective. So this is related to the your paper on private distribution learning with public data, the view from sample compression. So this question is from Saqib Chowdhury. He's asking, could your method work well with the public data? Could your method work well if the public data and private data come from slightly different distributions?
Yeah, so a little bit more context here. I've already talked about how, say, like public pre-training of machine learning models can be very useful in terms of getting better downstream performance in terms of private models. And so what we did in this paper and a few papers is we looked at very sort of simple, fundamental theoretical settings where we theoretically demonstrated that public data can be very useful in improving the amount of data you need. You need much less data if you have a bit of public data. And so to answer this specific question, asking whether it still works if public data and private data come from slightly different distributions, is still effective. And to specifically answer that question, yes. We have some ways of we have some results in that paper, which are not the main focus, showing that even if there's some sort of distribution shift or robustness to some outliers, then it's still okay. But more broadly speaking, I think I see it more as a way of kind of confirming that what we already know empirically, that in many cases, you don't need an exact match between your training data, which is public, and your training data, which is private. They can, as long as they're sort of at least coarsely related, there's some relationships between the data, then you're still extracting useful information.
Okay. And this is regarding your paper on detailed overview of inaugural generative AI and law. I believe it was in a workshop. And this question is from Pratyusha Pingili. So the question is, what specific techniques or resources may be employed to guarantee efficient communication and mutual understanding between ML researchers and legal practitioners, given the difficulty of developing a shared knowledge base between the domains of machine learning and law? Existing platforms or frameworks that could be modified for this use, or should new ones be created?
Right, and like you mentioned, you alluded to this workshop. For a little bit more context there was a very nice workshop at co-located with ICML called Gen Law, which is focused on generative AI plus law. And this was trying to bring together people sort of from all ends of the spectrum, people who are legal professionals, people who are computer scientists who work on things like privacy, robustness, all sorts of things like this, and kind of anywhere in between. And I think this is very important as many of these tech issues become more prevalent in kind of the legal area. Just trying to build a shared understanding of what the challenges are, what the legal parts of the considerations are, things like that. And I think this is kind of one of the ways forward, by just bringing people together and also getting a type of shared knowledge base in this area. And I know people who have built up expertise in both of these areas. For example, one of my good friends and collaborators, Aloni Cohen at University of Chicago, he did a PhD in computer science, but he also has a lot of law expertise in terms of looking into implications of many of his algorithms or many legal implications surrounding some of these considerations. So he's also published in legal journals as well. So I think an important way to move forward is having people who are experienced and have expertise in really both of these different fields, because having knowledge at the intersection, I think, is almost essential to make any sort of progress here.
Okay, and the next question is from Lindsay Rebello. This is on the paper, not all learnable distribution classes are privately learnable. So her question is, how does the trapdoor distribution class presented in your work relate to the known challenges in pack learning under differential privacy?
Cool. So yeah, like there's many classical statistical and learning tasks people have studied in machine learning and machine learning theory. One of the more classic ones is pack learning. Pack learning is, a fancy way of saying, first of all, it stands for probably approximately correct learning. And roughly speaking, it's a way of formalizing what it means to learn a function. And this has been studied a lot in both the private and the non-private setting. And kind of the very surprising thing is that learning becomes a lot harder when you require differential privacy versus without. As a kind of a canonical example, that if you want to just learn what's known as a threshold function, it's just one dimension. Say, if you have, say, a function where to the left of some point it's all going to be zeros, and to the right of the function, the point is all going to be ones. This is very easily learnable non-privately. I mean, just kind of takes a constant amount of data, but privately, there's prior work that shows that essentially this is not learnable at all. With no finite amount of data can you learn continuous thresholds. So what we focus on is a distribution learning setting, where we show similarly there's some classes of distributions which are very easy to learn without privacy, just say a constant amount of data, but there's no private learning algorithm. So thematically, this is related to pack learning in the sense that there's huge separations between what is and is not learnable with a finite amount of data. But at least from a technical perspective, it just seems to be, there's no real technical relationship that I'm currently aware of where, the results follow for the same reason.
Okay, and on the same topic, Samhita Mova is asking, your research refutes Astiani's conjecture on learnable and privately learnable classes. This is going to act as a fundamental limitation in private distribution learning. Does this mean we need to reconsider our approach to developing generic private learning algorithms? How will we be able to balance learning efficacy with privacy constraints in the picture?
Right, and there was a conjecture by Hassan Ashtiani, my friend and colleague at McMaster University, at least. He sort of conjectured that anything that is learnable without privacy, there should be a generic method that allows you to learn it privately as well. And he's been focusing on this agenda with some very nice papers, which shows in sort of more generic settings where this class is learnable non-privately. Well, we just run that non-private learner and do some privatization to convert it to a private learner. And so I guess the holy grail of that line of research was ideally you should be able to design a method which would take any sort of non-private learning algorithm and convert it to a private learning algorithm. Unfortunately, we refute that conjecture, showing that there's no such fully generic learning algorithm. So the natural next step is to try to figure out what sort of natural subclasses of distribution, what problems do we actually care about, and based on additional structure that these cases we care about might hold, is there a way to convert a non-private learner to a private learner in those restricted cases?
Okay, thanks. So the next questions are from the paper, The Discrete Gaussian for Differential Privacy. And the first question is from Xingrong Ma. She's asking, are there any specific scenarios where the discrete Gaussian might face limitations compared to its continuous counterpart? And there's also a question by Sugandha Chavan related. Many differentially private systems use continuous distributions. How easily could the discrete Gaussian mechanism be integrated into existing systems that currently use continuous distributions?
Right. So I kind of said this during, sorry, I told you already what the discrete Gaussian is during the intro talk here. But to just recall, it's essentially saying that you add discrete Gaussian noise to some sort of count and output the result. So this is relatively new. And the more classic way people do it is just add continuous Gaussian noise to a count and then output the result. So you can see that they're related, but they're not exactly the same. And so the question they're kind of asking, what's the differences? Why would you prefer one versus the other? And so there's a few reasons why you might prefer the the discrete one, and some reason you might prefer the continuous one. First of all, like we proved in our paper that they both enjoy roughly comparable privacy guarantee. That is, if you output a sample from the continuous versus the discrete Gaussian, they'll roughly guarantee the same amount of privacy for typical application settings. This is not universally true in the sense that there are some parameter regimes where there can be a gap. So, in these cases where there's a significant gap and it's much less private, then you might not want to rely on the discrete Gaussian there. Another thing can come up with the idea that the reason why you might prefer the discrete Gaussian is because of the fact that the continuous Gaussian is susceptible to certain type of numerical precision attacks. In fact, using things based on floating point arithmetic, this results in the fact that on a computer, what a continuous sample from a Gaussian ought to be is not actually the case of how it's represented in the computer. And so these sampling, which are inexact because of floating point issues, they may be attackable. So consequently, switching from continuous to discrete Gaussian can be advantageous to avoid this type of vulnerability. Now, I'll say that in pretty much any case you use the continuous Gaussian, you can just use the discrete Gaussian instead. So that's convenient. And you just have to change, say, a few lines of code. The downside is that the libraries for, say, sampling from this distribution are not as mature as they are for the continuous Gaussian. So there may be time overheads. There may be some implications for people doing downstream data analysis. They might have to change their methodology a bit based on it being from a discrete rather than a continuous Gaussian. But generally, it is intended to serve as a drop-in replacement.
Okay. And the next question is on your paper, Privately Learning High-Dimensional Distributions. The question is from Vaishnavi Nanduri. She's asking, how could the recursive private preconditioning method be extended to other high-dimensional distributions beyond Gaussians and product distributions?
Right. And in that paper, we give a sort of generic recipe, which is something we call private preconditioning, which is a fancy name. But really, what it means is how do we, at a very coarse level, find the shape of what the distribution looks like? It turns out having a coarse understanding of what a Gaussian looks like, there's many different types of Gaussian. It could just be totally spherical. It could be very elongated. And this private preconditioning method tries to get an idea of which of those cases it falls in. Is it, what the shape of the distribution is. It's hard to say in the abstract how to generalize this to any other case. But if you give me a specific case where you'd want to know what your shape of your distribution is, I would wager that very similar techniques work. You just have to exploit some of the structure in that specific setting to try to find out the shape of the distribution in a similar way.
Okay, and the next questions relate to your paper, Actively Avoiding Nonsense in Generative Models. The first question is from Lingling Chen. She is asking, as AI continues to advance and model training improves, there's a growing concern about the possibility of AI gaining autonomy and slipping beyond human control. I think she is referring to the famous fears expressed by the big people. How can we ensure that while pushing forward with the development of AI, we simultaneously safeguard human safety and upload ethical standards?
And yeah, this is another, I guess, big picture question, which a lot of people are very curious to know the answer, and a lot of people are invested in. And I think, again, the answer is that I don't think anyone really knows the truth for sure, or the right answer for sure. One way is via legislation, for example, laws which act as safeguards. But of course, these are very controversial. For example, like I mentioned before, this SB 1047, which was vetoed, a big part of that was AI safety, making sure, AI models aren't too big, whatever that means, making sure that they have off switches. Yeah, so I think legislation is one way, which is, of course, very contentious. But I think, at least from my own perspective, as a little bit more of a theorist and a specific researcher, is just understanding how these models work better. For example, a very, very specific negative behavior that we want to focus on is issues, like I mentioned, with privacy, making sure that these don't spit out training data or reveal sensitive information. Yeah, I think being able to identify these small pieces of this very, very broad question is important as the first step. And then after you identify the specific things that might feed into the bigger picture question, tackling them one by one. And I think one way to do that is through rigorous definitions of what you mean. So like just to take this apart, the big picture question is how, can AI destroy humanity? One specific way is due to loss of privacy. And from there, we can take a moment to formalize what we mean by privacy, which is, going into differential privacy as well as many other notions of privacy. And then from there, once we've gone to differential privacy, we can come up with algorithms and techniques which preserve differential privacy. So it's, again, too broad a question to give a totally satisfying answer to, but I think breaking it down into smaller bite-sized pieces and trying to address those one by one is what at least I feel like I can do as a researcher, and maybe some of other people in the audience as well.
Yeah, that's a good perspective. And related to that same paper, Hamsalakshmi Ramachandran is asking, what are the main challenges in developing a computationally efficient validity oracle? And she's clarifying that a validity oracle can help the learner identify what it should avoid generating.
Right. So this is a question that has to do with a paper we had actually from 2018. So this is kind of before the rise of large language models, prior to, BERT and GPT style models. The focus of this paper was just trying to understand generative models and how to learn generative models, which, in addition to being good at modeling the distribution of data that it's intended to, also how to make sure it generates things which are valid. As as an example, say we train a generative model to output code, we would want it to output code which is, say, which would actually compile, not just random code snippets which aren't valid, Java, C++, Python, whatever. So one part of the framework that we introduce is you need some way to actually label examples or outputs, for example, whether they are actually valid or not. And so we say this in the abstract, but to make it a little bit more concrete, you can think of this example that I just gave, for example. It's possible to check whether a code snippet is actually valid. And for that type of setting, it's very easy to imagine, you just feed it into a compiler and see whether it compiles or not. For other settings, though, it might be a little bit more challenging. Maybe you have to ask a human expert, okay, is this valid or is it not? And in some sense, I don't know exactly how ChatGPT works. They're a bit mum on some of the details, but a combination of these types of techniques is actually part of these modern AI systems. For example, the RLHF, or reinforcement learning with human feedback, in some sense, acts as a type of validity oracle in the sense that it sees which type of string people prefer. Similarly, I think these are integrated with external tools like, compilers and stuff to see whether something compiles, or searching external data sources. So there's a variety of different ways someone could develop validity oracles. It really depends on the setting and what it means to be valid.
Okay, and a related question she's asking is, could you give a few real-world examples where the VGM framework would significantly do better than traditional generative models? I think by VGM, she's referring to validity generative models.
Yeah, exactly.
Yeah.
Valid generative modeling, or any variation of that. Yeah. And I think these examples that I gave, for example, if you trained a code snippet just by taking in a lot of code, you trained a code generative model which just takes a lot of code snippets, and it's pretty likely that it's going to generate much good code, but also a bunch of nonsense code which wouldn't even compile. And so by having something which tries at least to enforce the fact that it outputs only valid code, I think that's a clear benefit. But also really any type of setting where the outputs may not make sense.
So just curious, how is this VGM framework differ from RHLF? RLHF, sorry. Yeah.
Yeah, I mean, how the specifics of the details are, the specific details of how it's implemented are kind of different, but I would say at least as a principle, I think it's quite similar in the sense that both RLHF and our VGM type approach are very much just looking at looking at the outputs of what the model could generate and trying to figure out which ones are preferable or not. Where I think they formalize that as, given two outputs, which one is a better answer to the question, whereas we formalize it more on just, is it valid or not? So I think it's similar principles, based around the broader framework known as active learning, where you kind of get labels on demand for some potential data points. So yeah, I think there's conceptual links, but no specific technical links I am aware of. I guess RLHF, I don't know what year exactly was. It was maybe like 2020 or 2021, somewhere around there. Whereas our paper is from 2018. I don't think they probably weren't based on ours. It's not a super well-known paper, this one in particular, but I think it's a natural idea that a lot of people, coalesced around.
Oh, okay. So you just proposed the idea of validity in a generative models.
Exactly. Yeah. Like we want a generative model, which additionally will have a high chance of outputting something valid. And what are some algorithms and ways to do that?
Okay. And the next few questions are from your paper. Remember what you want to forget, algorithms for machine unlearning. And the first question is from Shazid Sheikh. And he's asking, in scenarios where data unlearning requests increase exponentially due to stringent privacy compliance requirements, what strategies can be implemented to maintain the model's predictive accuracy and overall performance? How can we balance the competing demands of extensive data removal and preservation of model utility?
Yeah, this is a really hard question in the sense that his question asks about very, very broad settings, like in sort of production settings where a lot of requests come in and a lot of changes have to be made, maybe even on a daily basis. But especially as a theorist, sort of I like to focus on the simplest setting that we don't know how to solve. And even in sort of a one-shot setting where there's one request to delete some batch of data points, we don't even know how to solve this much simpler question. So I would say that, first we have to solve that problem where we just try to understand how to do a single unlearn request for a large collection of points. And then from there, maybe we can think about these more dynamic settings which are closer maybe to production pipelines afterwards.
Okay. And the other question is on the same topic, is from Kanchan Nayak. she's asking, how can we adapt algorithms and results presented in the study to other areas, such as responsible AI for algorithm fairness to overcome biases or non-convex problems?
Yeah, so non-convex problems, as I sort of said
Yeah,
before, is just a setting we don't really know how to do. And that's kind of like the big picture question. The techniques in that paper, at least, are not immediately applicable to that setting. And I think everyone cares about how to actually do it. That said, for like responsible AI, for algorithmic fairnesses to overcome biases, I'm not immediately sure of like, how to relate the two. I could say that maybe there may be some ways to, okay, like here's a potential way to overcome biases. In some certain settings, maybe changing the mix of your training data is a common way, and just retraining a new model from scratch on this new data set, which may better account for the biases present. So the type of techniques that we show there are in some sense a way of editing the model without retraining it from scratch. So there may be ways in order to use these type of ideas, or more broadly speaking, ideas in the machine learning literature on how to do model editing rather than retraining from scratch. But I think I don't know any specific links right now.
okay. And to elaborate, to elicit more information on that, I believe there's a related question. How might your unlearning framework be extended to handle more complex deletion requests, such as removing all data associated with a particular feature or attribute? And we have been focusing only on the rows. How about the columns, like the features?
I see, like removing a feature. I guess I'll say that if you can kind of identify or clearly define what the problem is, then it's easy to do it. For example, suppose you want to remove all data from the data set, which is which has, say, like a specific feature, a particular value for the first feature. What you could do is simply go through your data set, identify the rows which have that specific property, and just unlearn that entire set of rows. But maybe you're suggesting something slightly different, in which you just want to kind of forget a specific feature or attribute of the data. And I think this is a bit less clear, even forgetting unlearning, simply trying to be private to a specific feature rather than with changing of the rows. I think this is not like it's not well defined or well understood even in the, say, privacy setting. So yeah, I don't think I have a good answer for that question.
I think it's a good research gap to fill because I mean, considering fairness aspects of the model, if some model is trained on protected attributes like gender or things like that, we would want to eliminate the entire feature, right?
That's true, but I guess one of the things that's difficult to account for is the fact that often there can be correlations between certain features. So even if you sort of try to forget the influence of one feature, it's possible to infer through the value of that attribute through another feature. So even defining the problem is a little bit tricky.
Yeah, that's right. I agree. And the next question is from the paper Robust Estimation of Random Graphs. Um, So the question is from Manjot Singh, and he is asking, can the proposed robust estimation techniques be adapted or extended to handle other random graph models other than Erdoas Renyi? If they can, what is the best way to do so?
Cool. So in that paper, what we did was we focused on a very sort of like almost trivial question in the non-robust setting, which is, you have one realization of an Erdos-Renyi random graph, which is a very basic random graph model. Essentially, it says that every edge is selected to be present in the graph uniformly at random with some parameter p. And so the question is, how do you estimate this parameter p given a realization of the graph? So in the non-robust setting, you can just count the fraction of the edges that are present. It's very simple. But in a robust setting where there may be an adversary who changes some of the edges in some specific way, which we define in the paper, it is still possible to. And so we have an algorithm that shows that even in some robust setting, it's possible to estimate the value of the parameter. And I guess the question is asking whether there's more broad settings which this can be applicable. I thought about this a bit myself. I just don't know what other interesting random graph models there are that are in some sense related where you might want to solve a parameter estimation problem. There's some work done by others on the problem of estimating what are known as graphons, which are a generalization of stochastic block models. So there's some algorithms that look at robustness in those types of settings. But I don't know of any other interesting generalizations of this model. So if anyone has ideas of interesting robust estimation settings in random graphs, please send me an email. I'd be happy to think about it. I just don't. I'm sort of a little bit separated from people who actually do random graph models in terms of modeling real data. So I'm just not sure what are the interesting cases to study.
Okay. And the next question relates to your paper, Avoiding Pitfalls for Privacy Accounting of Subsample Mechanisms Using Composition. This question is from Karisma Tamarana. She's asking, what impact do the findings in the paper about privacy differences between Poisson subsampling and sampling without replacement have on current machine learning models using differential privacy? And how should professionals adjust their privacy methods?
So what this question is asking is, there's like, when doing a differentially private machine learning, there's like a specific algorithm that people are meant to follow. But the thing is, people might make some little tweaks to this algorithm based on what's convenient for their practical settings. For example, to give you the biggest example, which is the one that we sort of investigated in this paper, the way that differential privacy machine learning is supposed to be done is when you sample a batch for a step of SGD, what you're supposed to do is sample each data point to be in your batch uniformly at random with some particular probability. This is known as Poisson sampling. But this is a rather complicated primitive to implement. It can be time-consuming, memory intensive, and so on. So instead, what people do is they often just do the typical batch loading, which is, permute your data set and take them sequentially, which is sometimes known as shuffling of your data set. This might seem like an innocuous change, but roughly speaking, one of the things we show in our paper is that there can be significant gaps between different ways of how you form your batch, in the sense that doing one way of selecting your batches might give you very strong privacy guarantees, whereas doing another might give you much weaker privacy guarantees. So the guidance we kind of give is that, be honest and say what specific methods you're using for your algorithm and use the corresponding method of privacy accounting to say honestly how private is this method, rather than just doing whatever and hoping it won't make a difference, because these rather seemingly inconsequential implementation differences can actually make a big difference.
Okay, and the next questions relate to your paper, CoinPress, Practical Private Mean and Covariance Estimation. Apparently, this paper introduces a new method for estimating the mean and covariance of multivariate sub-Gaussian data while ensuring differential privacy. And this question is from Aishwarya Gulab Thorat. And the question is, what are the primary challenges in extending CoinPress to estimate higher order moments like skewness and kurtosis while maintaining differential privacy? And how might you approach these challenges?
So in this paper, we focus on estimating first and second order moments and like the mean and the variance of a distribution. But we give a sort of general recipe, a framework for type of addressing these problems. So in principle, using the same type of framework, it should be possible to estimate higher order moments as well. The caveat is just that often estimating higher order moments can be more data intensive. Roughly speaking, the amount of data needed to estimate the kth order moment is exponential in k. So, you need more and more data to estimate any higher order moment. And also, there is not as often a requirement to estimate these higher order moments. Like, for example, mean and covariance are often things that people care about, but I think there's less demand to know precise information about higher order moments.
So these methods are accurate, or are they like DGIM and things like that? Are these approximate, or?
I'm not so familiar with DGIM and what you mean by that.
So typically in streaming data, we employ a different kind of techniques for estimating moments. So apparently these are exact estimates, right? These are not like.
I see what you mean. Okay, yeah. You're referring to, I think, a setting where you have a stream, and ideally you would like to estimate the stream's moments exactly,
Exactly.
but you
Right.
frequently have to rely on streaming or sketching methods, which maybe approximately output the stream. So
Yes.
the distinction I want to make here is that at least when I care about private estimation, for example, if you want to estimate the mean of a distribution, rather than the mean of a data set, you can never estimate the mean of the distribution exactly because you're only going to get data sampled from that distribution. So even at the sampling step alone, there will always already be some approximation present. Similarly, whenever you do differential privacy, there always has to be some error. So like, again, you'll get some sort of approximate measurement of the parameter. So yeah, there's kind of no hope. The exact estimates of these moments, either lower or higher moment, isn't really the type of thing that we focus on because we're looking at estimating properties of a distribution rather than the data itself.
Okay. And the next question is related to your paper, exploring the limits of model-targeted indiscriminate data poisoning attacks. The question is from Himani Shah. Can the attackers still poison models in federated learning? Because federated learning is when data stays on user devices and only the model updates are shared. I wonder if your poisoning methods can still work when attackers don't have full control over the training data, as federated learning is becoming popular, especially for privacy reasons.
Right. And in this paper, we focused on sort of a data poisoning method. Wherein we sort of focused on a centralized setting where the attacker can modify some fraction of the training data. And the question is, how does it influence the downstream trained model? In principle, it should be effective still in a federated learning setting where maybe there's just a fraction of malicious users rather than, the centralized setting, which I just mentioned. So yeah, we haven't done it, but I don't really see any obstacles that are in the way of mounting a similar type of attack in a federated learning setting.
Okay, and a related question is, how does the poisoning method work on simpler models like decision trees or support vector machines? So apparently in this paper, you used only complex models like neural networks. So the this Himani is curious if the same poisoning threshold idea works for these simpler models also.
So the short answer is no, because they're kind of like very different type of models. In our paper, we focused on neural networks and sort of as well as the simplest type of neural network, which is logistic regression. Typically for these other models like SVMs or decision trees, they're going to have very different types of properties. I would say some of these models are much better studied than neural networks. For example, SVMs, they've been studied actually way back on how to do data poisoning attacks in a very nice paper of Biggio et al. From ICML 2012. Actually, this was one of the Test of Time awards in ICML 2022. So it's been a very influential paper, and they kind of give a much better understanding about fundamental settings like SVMs. But we've sort of tried to specifically focus on more complex settings, which are like neural networks, which typically seem to be harder to data poison compared to SVMs and so on.
Right, makes sense. And the next question is on your paper, private mean estimation with person-level differential privacy. Apparently, this paper introduces new algorithms designed to estimate means while maintaining strict privacy protections. The question is from Prasad Pramod Shimpatwar. Um, he is asking, in your paper, you address a challenge of balancing privacy and accuracy. Could you explain the specific trade-offs your algorithms encounter when adding noise to maintain person-level differential privacy?
So in pretty much any setting, there's always going to be a trade-off between privacy and utility, in the sense that if you want perfect privacy, then you have to completely ignore your data. You just don't output anything. This is totally private, but not very useful. And on the other end of the spectrum, there is perfect accuracy, where you don't add noise. You just output the statistic as if you weren't using differential privacy. So like the trade-off is somehow figuring out how to balance those two and landing somewhere in the middle, where you add noise or introduce some sort of other techniques in order to have both privacy and accuracy at some intermediate level. Specifically in this paper, I think one of the techniques that we focus on is understanding how much influence clipping of your statistic can introduce error. It turns out that clipping is a very important step in many private algorithms in order to limit the amount of noise you have to add. And so there's kind of a trade-off where the more aggressively you clip, then the more error you introduce due to bias of your statistic. Whereas on the other hand, if you do less clipping, there will be more noise required and you'll get more error that way. So we try to focus on how do you find the sweet spot where you don't introduce too much bias, but you also don't have to add too much noise in order to get the best level of privacy and utility.
So that's more like a hyperparameter, right?
Yeah, it's kind of like figuring out which hyperparameter for the clipping radius is the best way to maximize utility, yes.
Okay, and the next question relates to your paper, disguised copyright infringement of latent diffusion model. Apparently, it highlights a critical issue at the intersection of AI and intellectual property law. And the question is by Pranav Ravindran. So he says, your paper demonstrates that copyrighted content can be hidden in visually dissimilar disguise images, yet still be reproduced by latent diffusion models. How might this affect the legal definition of access to copyrighted material in the context of AI training? And do you foresee a need for new legal frameworks to address this form of indirect access?
Yeah, it's a good question that people are generally wondering how to deal with copyright infringement when it arises and when it doesn't arise. First of all, I'm not a lawyer, so I can't claim expertise on all aspects of this, but I guess the main conceptual message we have is the following. So one reasonable way you might think of trying to audit a machine learning pipeline to find out whether some sort of private copyright infringement occurred is, you know, be given access to the training data, look at the training data, see if it all looks kosher, none of it's copyrighted. Then someone trained the model on it and, you know, it's fine. I guess what we raise is the fact that, you know, directly looking at the training data, the immediate training data, is insufficient to determine whether these types of copyright infringements occurred. You know, to say it a different way, it could be that there's a data set where if you look at it, then it's not clear that there's any copyrighted image in this training data set. However, if you train a model on this data set, it would behave similarly to a model which was trained on a data set that includes copyrighted images. So the way that this is done is by hiding sort of the copyrighted data in the latent space of some of these inputs. And so this sort of prescribed that we should take a more broad look at how we audit machine learning models, rather than just looking at the training data that goes into a model, also looking at where did that training data come from, how was it designed, and so on. So we kind of make a very narrow prescription there rather than trying to go for anything too broad. By the way, I probably have to take off fairly soon, so maybe if we could just do a couple more questions.
Yeah, I know I took a lot of your time. Probably this will be the last question then.
Cool.
This question is from Sri Karthik Nandam, and he's asking, how do you envision extending your sum of squares exponential mechanism to other statistical tasks or machine learning problems beyond mean estimation? I believe this relates to coin press, so the same paper that we talked earlier. Are there promising avenues for applying this approach to more complex estimators like covariance matrices or higher order moments? Yeah.
This is a great question because I get to tell you about one of my favorite private algorithms. So typically when people design differential privacy methods, they usually just do some sort of very simple noise addition, like adding Gaussian noise, Laplace noise, or something like it, which is a very simple to implement and usually does okay. But there's another algorithm which is known in the differential privacy literature, a framework known as the exponential mechanism, which is a little bit more complicated in the sense that it is instead sampling from a distribution of outcomes rather than adding noise to a statistic. So it's a little bit harder conceptually, and importantly, it's much harder to actually run in the sense that frequently when you run the exponential mechanism, it is an exponential time algorithm. It's not something that's computationally efficient at all. So what we do in one paper, it is actually different from the coin press, a subsequent follow-up work we did, is we make a theoretical algorithm, which is computationally efficient for some mean estimation problems. Now, when I say theoretically, a theoretical algorithm, this is not something that you could actually run on a real computer, but if you do the analysis, it's technically polynomial time. So I think probably one of the most interesting research future directions, I think, is finding out, are there other settings where you can use the exponential mechanism to do differential privacy, and in particular, can you do it computationally efficiently? Yeah, and actually computationally efficiently in a practical way that you could run, because it usually gives very, very good utility, but it's just not efficient to run. So figuring out ways to surmount that efficiency barrier, I think, could give dramatically better algorithms if you could do it.
And can this be integrated into machine learning algorithms easily or?
Yeah, it could be because a lot of my research focuses on, say, mean estimation. But when you think of it, machine learning, when you do train them, you use SGD, and SGD is really a sequence of mean estimation algorithms. In some sense, simplifying a bit, training a private machine learning model amounts to a sequence of private mean estimation problems. So, any sort of method you use for private mean estimation could also be implemented into private machine learning model training in a similar way.
Okay. So thanks a lot, Gautam. That was really very insightful. I think we got a lot of answers, very insightful answers. So I'd like to thank you with this small token of our appreciation. So if you were in person, then if this was in person, we could have presented you with a memento, but I wanted to present you this small token of appreciation from the chapter. Thanks a lot for spending a couple of your hours, valuable time, and hopefully we will stay in touch.
Cool, yeah, for sure. Thank you so much, Vishnu. It's very kind. Yeah, if anyone has any further questions, can feel free to follow up by email, and I'll try my best to get back to you.
Yeah. I don't see any questions on YouTube as well. I just checked, but let me check again. Yeah, there's no comments on YouTube. I mean, there are some comments which are not very relevant. So we'll end the session here. Thanks again, Gautam, and hopefully we'll see you sometime later as well.
Cool. Yeah, and same to you. Have a good IEEE day, everyone.
Yeah, thanks.
Bye-bye.
Bye, everyone.